So this is chapter 27. It's about special relativity. That's Einstein developed this. So you notice we're skipping chapter 26. So here we go. We want to understand how the principle of relativity leads to the relativity of simultaneity and length, and thus to time dilation and length contraction. Now that probably doesn't mean a single, it's probably crazy right now, but you'll understand what that means later. We'll use the Lorentz transformations of velocity. We'll explore relativistic energy and momentum. We'll recognize the significance of Einstein's famous equation E equals mc squared. Now, one thing before we get going. So it's called special relativity. It's called special relativity not because it's like special. It's special relativity because it's restricted. So special relativity is restricted to motion where A equals 0. That's okay, so velocity is constant. Einstein figured this out first, and then after he figured that out, he did where he could have acceleration not equal to 0, and that's called general relativity. We're not going to talk about that. Okay, now I have to warn you, this is a very, very long chapter, and conceptually it's very, very difficult. And the reason it's difficult is because it disagrees with common sense. So it disagrees with your common experience, disagrees with your common sense. So it's hard to get a grasp on it because it doesn't make any sense. But you just have to let the experiments and the logic and the mathematics lead the way. Okay, so please watch this video clip. It's only a minute, 30 seconds. But just let me tell you what it is. So it starts out, you see this airplane in the sky, and then it lands, you know, in the airport. And so, you know, you're thinking, whoopee. And then next thing you know, there's a man who comes with a cleaning rag, and he starts cleaning the airplane. And the airplane is actually only this large. So you think it's a regular airplane, but it's a model. And then there's a similar thing with a castle. You think it's a real castle, and then you see some little children around it, you realize the castle's only this high. And so what you're supposed to get from that is this. Things around us aren't always what they seem. And that really applies to relativity. And you'll see that. But try to watch it. It's really cool. Okay, so what I'm going to do now, I'm going to give you a brief history lesson. And we're going to discuss most of this later on in gory detail. But I just wanted to give you kind of a heads up. So, I mean, the question is, what led Einstein to develop special relativity? Because he pretty much did most of it all by himself. So let's talk about that. All right, so, okay. Now, we're going to have to review some Physics 105. So Physics 105, hopefully you remember it. At the time of Galileo or Newton, there was something called the principle of relativity. The laws of physics are the same in all inertial reference frames. Now remember, inertial reference frame means A equals 0. By the way, we still believe this. It just means, you know, like if you did an experiment in this room, you know, throw a ball, you know, it's going to go in a parabola and all that good stuff. Or let's say you're in a moving train. As long as a train is not accelerating, you know, you throw a ball and it still undergoes parabolic motion. I mean, everything is the same. You could do an experiment here. You can do an experiment in a moving train, moving jet. I don't care. As long as you have this, you get the same results. Well, no kidding, right? You do an experiment in Russia. You do an experiment in La EA. You get the same results. No kidding. So everybody believes that. Everybody still believes it. Okay, and we talked about that in 105. Okay, by the way, Galileo, he was like 1600s, so way long time ago. All right, so that was the principle, right? And then you know, Galileo and other people, they developed the mathematics. So two reference frames. We have reference frame S prime, which moves to the right with velocity v. It moves relative to reference frame S. Now here's the important thing. We don't know anything about reference frame S. It could be moving, it could be at rest. We don't know, we don't care. The only thing that's important is that S prime moves to the right relative to S. Okay, and here's a particle, right? So it says the velocity of this particle is measured to be v in frame S in V prime in frame S prime. So I was going to use primes in the S prime reference frame, like X prime and Y prime, and no primes for S, so X and Y. That's all. All right, and we figured that out in Physics 105. So the velocity of something in S equals the velocity of it in S prime plus the speed of the reference frame. Now that's not a big deal. You all know that from your experience. So let's say I have a car moving, all right, let's say the car is moving at 100 miles per hour. And then somehow somebody stands, you know, it's convertible, and throws a ball at 60, well, let's switch it. Let's say the car is going at 60, and we throw the ball at 100 miles per hour. And we're ignoring air resistance, right? So the car is going 60 miles per hour relative to the road, and the ball is going 100 miles per hour relative to the car. So if I was standing on the road just watching this, what would I say is the speed of the ball? Well, it's 100 miles per hour plus 60 miles per hour, so it'd be 160 miles per hour. So that's pretty much common sense, right? Okay, and we talked about that again in 105. So that's all this thing means, you know. This is the speed of the ball in this reference frame. This is the speed of the reference frame, right? So this is like this is the car, 60 miles an hour. This is the ball, 100 miles per hour. So you add them, and you get the speed according to this reference frame. Okay. So Galileo worked out, you know, he figured all that out. He also figured out the other transformation equations. So everybody assumed that the time in this frame was the same as the time in that frame. Since this is only going in the x direction, the z coordinates are the same, the y coordinates are the same, and this is just the opposite of what I just showed you. Okay. Oh boy. So this, let's say this is x prime. So x prime is x minus this, right? This is vt. This is how far this thing travels in a certain amount of time, right? So this distance is this distance minus that distance. That's all that is. And again, that's just review. So this is nothing new. All right, so we studied that in gory detail, 105. Now let's go back to 106. It's not supposed to be there. All right, so Maxwell, and we learned this a while ago, he was the person who figured out all the theory of electricity and magnetism. And don't worry about these equations. I just wanted to show you these because, you know, we already talked about these in 106. But he's the guy that came up with the mathematical theory. And hopefully you remember, and he's the guy that said that the speed of light is a constant, and it came from his equations. Now, there was one thing that was really, really, really bad about Maxwell's equations. They were incompatible with the principle of relativity. In other words, according to what people thought back then, the laws of physics, mechanics, like throwing a ball, but not electromagnetism, are the same in all inertial reference frames. Now, that's completely insane. Because, I mean, you know, if you do an experiment with electricity and magnetism here, and then you do it like on a moving train or an airplane or something like that, as long as A equals 0, do you notice any difference? Of course not. Does a computer work on an airplane? Of course it does. Does an iPhone work in a car? Of course it does. So this was really bothersome. And nobody could figure it out, but it was really, really bothersome because it didn't seem to make a whole lot of sense. All right. But like I said, nobody could figure it out, so they just let it go until Einstein came around. So Einstein, you know, he thought about this for a long, long time. And he said, this is nuts. The principle of relativity has to hold for everything. You know, mechanics, electricity, magnetism, everything. Okay. Well, so so that's what he based his ideas on. He said this has to be true. So then he thought, well, maybe the problem is with the Galilean transformation equations, you know, these things. Maybe that's where the problem is. Maybe electricity and magnetism do obey the principle of relativity, but maybe the equations that Galileo came up with are wrong. Okay, so what Einstein did, he figured out his own equations, all right? His own transformation equations. And he was able to use those to show that the principle of relativity says that all the laws of physics, mechanics and electromagnetism, are the same in all inertial reference frames. So that was awesome. Now, it's kind of funny, though, because the transformation equations are called Lorentz equations, not Einstein equations. Why? Because there was a guy called Lorentz who had already figured them out, but he didn't really know what to do with them. It took Einstein to take the next step. Okay, now, there's a huge price to pay if you're going to use these Lorentz transformation equations. And we're going to talk about this in gory detail. Basically, the Lorentz transformation equations show that mechanics is wrong in that space and time are not absolute, they're relative. What does that mean? Well, is this large or small? Well, compared to an atom, it's really, really large. Compared to the sun, it's really, really small. So we say that size is relative. Well, what I'm saying is that time is relative, and space is relative, and some other things. So, for example, if I'm moving relative to you, and let's say somebody sneezes, so you'll say the sneeze lasted, let's say, 1/10 of a second. I will say a different amount of time. Same sneeze, and we're both right. We'll get different measurements for the time of the sneeze, and we're both right because time is relative. Here's another thing. So here, this is a meter stick. So if I'm running relative to you, you know, I say it's a meter. It's a meter long, right? Because, you know, this is not moving relative to me, so it's a meter long. But you would actually measure something less than a meter because size or distance is relative. Now, why don't we notice this in everyday's world? Well, because you only notice these things as the speed of the object, it gets close to the speed of light, which is, you know, really, really fast. Okay, also, Einstein showed that our friendly velocity equation here is wrong. We need to fix that. There's no such thing as absolute simultaneity. Mass is equivalent to energy, on and on and on and on and on. So, you know, there was a huge price to pay to make electromagnetism compatible with the principle of relativity. So, all right, so these are the Lorentz transformations. What's in yellow is what Einstein added. And we'll get to this gamma pretty soon, don't worry. But anyway. So a lot of things had to change. So you're supposed to be super impressed, all right? Okay, so that was the history lesson. So now we're going to go into gory, gory detail. So the first thing we want to talk about are reference frames. And you've seen this before in Physics 105. Reference frames. So this is right from 105. You are driving to town on H1. The speedometer in your car reads 45 miles an hour. I'm also driving to town on the same section of H1, and since you are driving so slowly, I pass you. The speedometer in my car reads 60 miles an hour. What is my real speed? So students, pause your video and figure this out. All right, so what did you vote for? Hopefully number 3. It's a meaningless question. Why is it a meaningless question? Because you have to say relative to what? Relative to a hummingbird, relative to me in the car, relative to the road. You've got to say relative to what? So basically, objects move relative to a reference frame. And you have to specify the reference frame. Reference frames are infinite in size. Okay, here's another one. You and your friend are comfortably seated on the French TGV as it moves quietly along the tracks towards Geneva, Switzerland at 300 kilometers per hour, pretty fast. Just before you both fall asleep, another TGV going in the opposite direction passes your train on nearby parallel tracks. Will you and your friend agree or disagree concerning the speed of the other train? So pause your video and figure it out. Okay, so what's the answer? You're both on the same train. So you both have the same reference frame. So what will you say? You will agree, right? You'll agree concerning the speed of the other train because you both share the same reference frame. On the other hand, you and your friend are comfortably seated on the French TGV as it moves quietly along the tracks towards Geneva, Switzerland at 300 kilometers per hour. Your type A friend decides it's time for a run and begins to sprint down the aisle. While she is sprinting away from you, another TGV going in the opposite direction passes your train on nearby parallel tracks. Will you and your friend agree or disagree concerning the speed of the other train? So please pause your video and figure this one out. Okay, now notice you're sitting down on the train. Your friend is sprinting away from you. So you have different reference frames. So what are you going to say about the speed of the other train? They're going to be different. Going to be different. So here's the important thing. Well, a couple. Okay, remember, objects move relative to a reference frame. A reference frame is infinite in size. 2, all experimenters at rest relative to each other share the same reference frame. 3, experimenters moving relative to each other do not share the same reference frame. So you want to remember that. Okay, so that was the concepts. Now let's do some of the math. So this is a slide from 105. So again, we know nothing about this frame, reference frame S. All we know that frame S prime is moving relative to S. So let's just read everything. All right, now, so the axes of S and S prime have the same orientation, right? Y is up, X is to the right. Frame S prime moves with the velocity V relative to S. The relative motion is parallel to the X and X prime axes. The origins of S and S prime coincide at t equals 0. So that's what we mean by t equals 0. So at t equals 0, both reference frames are right here. And then S prime starts moving away. But don't forget, we don't know anything about S. Okay. So here's a firecracker that explodes. So what are the firecracker's coordinates in the S prime reference frame? Well, obviously, X prime and Y prime, right? That's all, just X prime and Y prime. Okay, now here's what, I explained this a little bit a few minutes ago, but now I want you to figure it out on your own. So the coordinates of the firecracker in this frame are X prime, Y prime. What are the firecracker's coordinates in the S reference frame? So here's a couple of hints. S prime moves to the right with velocity V, that's relative to S, and S prime also moves for a time t. So I want you to figure out an equation, okay? I want you to, and I know that, look, the y's are the same, right? The y's are the same. So I want you to figure out an equation for x. So x equals something. And it's going to have x prime in it, it's going to have v in it. So pause your video and please figure out that equation. Okay, so remember, the origins coincide at t equals 0, so they're both here. Then S prime starts moving. It gets this far with velocity v after time t. So this is vt, this is x prime, so this is x. So you just look at it, right? So x equals vt plus x prime. All right, so x equals vt plus x prime. And again, the y's are the same because the motion is in the x direction. Okay, so these are the transformation equations that we studied in 105. We just figured this one out, right? But if you want to, you can solve for x prime, you get that. So those are the equations. Now, so these are the position equations. How do you go from position to velocity? Well, just look at the definition. Velocity in the x direction is delta x over delta t, right? So to go from position to velocity, you just take the change in the position over the change in time. Okay, so you do that, and you get this. So we're just doing fake calculus, to be honest with you, right? So these are the velocity transformation equations. Now you've got to be careful with the notation. This reference frame is moving with speed v. So you don't get confused, Randy Knight uses u for the velocity of the particle. Okay? So that means that this is the velocity of the particle in this reference frame. This is the velocity of the particle in this reference frame. And v is the speed of the reference frame. So you just got to get used to it. Okay, so you can see since the motion is in the x direction, the z's don't change, right? Because there's no velocity in the z direction, z direction. The y's don't change because there's no velocity in the y direction. The only thing that changes is in the x. And again, I already gave you an example of that, with the person throwing the ball out of the moving car. And that agrees with your common sense and your common experience. But we'll see later on that that's wrong. All right, so Galilean relativity, Physics 105. It works great as long as the speed of the object is much, much less than the speed of light. So here's an example for you to figure out. You ate Wheaties for breakfast today, a lot of Wheaties. It's supposed to give you a lot of energy. You are late for class, so you are running forward at 100,000 kilometers per second in our dream world, relative to the ground. So here's the ground, and this is you, and you're running at 100,000 kilometers per second. All right. Okay. A person standing still behind you, all right, shines a flashlight. Shines a light wave towards you at 300,000 kilometers per second, right? Speed of light. And then there's a person standing in front of you who also shines a light wave, right? At same speed. Okay? All right, so according to Galileo, all right, according to Galilean relativity, that at what speed do the light waves approach you? And again, this is the speed of light. Right? Okay, so pause your video and figure out the speed that this one's going to approach you, and that's you, right? And this one. So pause your video and figure it out, please. All right, this one is going in the same direction as that one. So according to Galileo, you subtract, right? So this one, the light is going to be coming at you at 200,000 kilometers per second. This one's coming towards you, so you add. So according to Galileo, this one's going to be 400,000 kilometers per second. And again, that's what we learned in 105. Right? Okay, so those are the answers, 200,000 kilometers per second and 400,000 kilometers per second. However, if you actually do the experiment, what's the answer? If you actually do the experiment, both light waves approach you at the speed of light, 300,000 kilometers per second. Now, if you think about that, that's totally insane, right? Because, I mean, you know, that's the speed of light. That's the speed of light. You would think if you're moving toward it, it would be larger. If you're moving away from it, it would be smaller. But when you, again, if you do the experiment, you would measure the speed of this light wave and this light wave to be the speed of light. So it's almost like, well, it's not almost, it's just like your speed is completely irrelevant. It has nothing to do with it. Everybody measures the speed of light to be the speed of light. Now, when you think about that, it's insane, right? And anyway, okay. So this is what it means. I'm just saying the same thing over and over and over again. So here's a flashlight. The light relative to this guy is the speed of light. Let's say that the train is moving in the same direction as the light. I don't care how fast the train goes. Let's say that the runner is traveling the same direction as the light, which is the same direction as the train. I don't care how fast the runner goes. If you're sitting on the street watching all this, you would actually measure the speed of light coming from the flashlight to be the speed of light. So how, I mean, it's basically, you're saying that the speed of the runner doesn't matter, the speed of the train doesn't matter. Everybody measures the speed of light to be the speed of light, which again seems totally insane. All right, so basically what does it mean? It means that these equations, these velocity addition or subtraction equations, do not work for light. They work for things that travel much less than, slower than light, but they don't work for light. So we're going to explain that mathematically, but we'll do that in the next video. So let's quit.